Hey guys, Jim Vanosky with Manufacturing Talks. Welcome back. A couple of years ago for Forbes, I wrote about the Giant Magellan Telescope, which is just a phenomenal story. Involves some pretty cool manufacturing stuff. Well, I've got Bruce Bigelow. He is the telescope's site infrastructure, enclosure, and facilities manager, and he's here to talk about the latest and greatest with that telescope and what it represents. And just really cool stuff. I definitely think you ought to stay tuned. Bruce is going to be with us in just a few seconds here on Manufacturing Talks.
Welcome to Manufacturing Talks with Jim Vanosky. Industry has a million cool stories, and Jim talks to the movers and shakers who are making them happen. Let's dive in.
Hey, everybody. Welcome back to Manufacturing Talks. I'm Jim Vanosky, your host. Really cool story today for the show. I've got Bruce Bigelow here. He is with the Giant Magellan Telescope. So this one's a very different kind of thing, but he's going to tell us how manufacturing fits with this amazing telescope that he and his whole team are building down in Chile. So welcome, Bruce.
Thank you. It's a pleasure to be here.
I'm glad to have you here. I wrote about this a couple of years ago, and I've kind of been following the story since then. And I know you've had a recent milestone we'll talk about. But, before we get into that, just want to hear about, what it is specifically you do, how you got into it.
Okay. Well, I have sort of a mixed background. I have an undergraduate degree in mechanical engineering, and I have a PhD in optical physics. And I started out my career working for a truck company, and moved, and then discovered a job working for the University of California observatories, which are based out of Santa Cruz, California.
Yep.
And I worked on astronomical instrumentation there for about 5 years, and became more and more interested in the optical aspects of how observatories work. And that led me to go back to school, to graduate school, where I got a degree in adaptive optics, which is an area of optical physics associated with correcting optical turbulence.
Mm-hmm.
And that's a key feature in fact, it's an enabling feature of the current generation of extremely large telescopes.
Yeah, right.
So that's where I've been and how I got here.
Yeah, which is very cool. I'm a mechanical engineer by degree myself, but then, I was kind of trying to keep up with you on the rest of it, because that's obviously some very high level knowledge that you acquired after that undergrad, which led you to the Giant Magellan Telescope. So tell us about what that is and what makes it so special.
Okay. Well, first, let me finish off my answer to this.
Oh, yeah.
The first question, which
Don't want to
was,
jump ahead.
I've actually been working for observatories for about 35 years now.
Oh, wow. Uh-huh.
So I've worked on the 6.5 meter Magellan telescopes, the 10 meter Keck telescopes, and I've actually done some consulting work for other observatories as well. So I have I've been dipped deeply into this very narrow niche of engineering for a long time.
Yeah. Yep.
Switching to the GMT, the Giant Magellan Telescope, it does have some really unique features. It's one of three what we're calling extremely large telescopes that are under development or construction right now. Another one is the 30 meter telescope, which is also based here in Pasadena, and the European Extremely Large Telescope. So there's three of these giant observatories under construction right now. Several of the things that make the Giant Magellan Telescope really special are the size of the aperture. It's effectively a 25 meter telescope. The optical prescription of the telescope, it's called a Gregorian, meaning that both the primary mirrors and the secondary mirrors are concave, and this optical design delivers a unique combination of field of view, image quality, and a useful focal surface. So the telescope, the optical design turns 1 arcsecond of angular resolution on the sky into 1 millimeter in the focal plane. And that means that the total focal plane area is about 1.2 meters. And we can procure and construct optics that can access that entire 1.2 meter diameter focal plane.
Mhm.
And that's a really unique capability for GMT. So we have this 20 arc minute field of view. We have very well corrected, meaning very high image quality across that entire field of view. And we're able to make use of all of it with instruments.
And it's going down in Chile. Explain why that
Yes,
is.
so Chile has, or very soon will have, the largest amount of collecting area for astronomical telescopes in the world. And it is the Chilean Andes are a unique environment. They are on the west edge of a continent, and they're reasonably high altitude. The altitude is good for reducing the amount of water vapor in the atmosphere that we have to look through. And the feature of being on the west coast, similar to the Hawaiian Islands, is that we have thousands of miles of Pacific Ocean where the air travels over the sea, and its temperature is stabilized by that time spent over the ocean. And so a mountaintop near the west coast of a continent typically has unique atmospheric conditions that provide for the best viewing of the sky.
Yep.
The Giant Magellan Telescope will go. We're building at an existing observatory site owned by the Carnegie Institution of Washington. It's called the Las Campanas Observatory, and the Carnegie owns about 100 square miles of property in
Wow.
Chile, which is the base for the observatories.
Yeah. And so, those of us who pay at least a modicum of attention to this know about the space-based telescopes, the Hubble, the James Webb. Essentially, what you're saying is you're overcoming some of the difficulties having a ground-based telescope that would, give you those advantages that the space-based scope has without having to lift a bunch of things up into
Absolutely.
space.
So our first, so the resolution of the telescope, its ability to separate two objects right next to each other, is purely, well, to first order, is a function of its diameter. And so it's much easier to build a really large aperture on the ground than to build one on the ground and then put it on a rocket and put it in space.
Yep.
So the JWST is a 6.5 meter telescope, James Webb, and the GMT is a 24, so 24.5 meter telescope. So we instantly have a four times better resolving power if we can correct for the disturbances caused by the atmosphere. And I know from your previous interview about the telescope optics that you're familiar with the fact that we've built the deformable optical system, the adaptive optical system, into the secondary mirrors of the telescope.
Yep.
Which means,
and it's what, is the tie for what I cover, obviously, is manufacturing. So you guys are making these things yourselves because you have the expertise to know what's needed. So yeah, go into the magic mirrors and what they do.
Yeah. Okay. So we ourselves is a interesting concept. So the University of Arizona is one of the founders of the Giant Magellan Telescope Consortium, and they have been developing the technology for spin casting, which is creating mirrors in a spinning oven. And they have developed that technology from a 2 meter to 4 meter to 6 meter to their maximum size now, which is 8.4 meters. So they have a unique laboratory in the world and a unique capability to create these single mirrors that are 20 something feet in diameter. It's a little hard to they're the size of a good sized swimming pool, each mirror.
Yeah, exactly.
So the University of Arizona has developed these unique capabilities to not only melt the glass into the right shape, spin the glass to create the optical surface, and then do the grinding and polishing of the mirrors to incredibly tight tolerances, millionths of an inch. And that's another unique feature of the Giant Magellan Telescope, is that all the extremely large telescopes are using segmented mirrors, meaning creating one large mirror out of many pieces. we are unique in creating our mirror out of 8.4 meter diameter pieces, and we have 7 of them.
Yeah, wow.
So that's
Amazing.
so the manufacturing of the mirrors, both the melting and creating of the mirrors and the polishing and finishing of the mirrors is done by our partner at the University of Arizona. The adaptive secondary mirrors are developed out of technology that came out of the University of Arizona. But the mirrors are being fabricated by one of our commercial partners in Italy. And those mirrors are really sort of a unique technological development as well. We're using a 4th generation design of this Ad Optica, is the name of the company, Ad Optica Adaptive Secondary Mirror. And the unique features of these are that they have basically an optical quality foundation that supports a 2 millimeter thick face sheet. So just to put this into scale, this is a 45 inch, 1.1 meter diameter, a sheet that's 2 millimeters thick.
Yeah.
So, at first glance, it seems like it must be an incredibly delicate thing. But each one of those mirrors is supported on 670 electromagnetic actuators. And it's those actuators that allow us to change the shape a couple thousand times a second on each of those mirrors in order to correct for the atmospheric disturbance caused by the light coming through our atmosphere.
Amazing. So how are you able to understand what's going on with the atmosphere to be able to make those adjustments in real time?
Yeah, I love that question. And one of the ways to think about this is that I think we're all reasonably familiar with is noise canceling headphones.
Mm-hmm.
And what the headphones have a microphone in them. They're sensing the noise around you, and then they generate a pressure wave in the speaker that is exactly the opposite phase of the pressure waves of the noise that are around you.
Yep.
And so there's a closed loop control system in a headphone, in a noise canceling headphone, and we have the exact same thing working instead of with sound waves, but with optical waves. So we point the telescope at a star or an artificial star that we make ourselves, and we measure the distortion a couple thousand times a second, the shape of that image to figure out what went wrong as the starlight passed through the atmosphere. And then we put the opposite error into the secondary mirrors to cancel out the error that the atmosphere caused.
Mm-hmm.
And for a 25 meter telescope, you have to be able to do that a couple thousand times a second to stabilize the image and then correct its shape.
Yep. Amazing. And so your location gets you a lot closer to being free of these distortions, and then your technology, effectively eliminates the remaining distortions that are there, right?
Exactly.
And so that gets you to kind of almost a space-based ability to perform, right? Except you're a much bigger instrument than we could ever have in space. So can you, in layman's terms, say, okay, how does this compare with other scopes that we hear about as far as performance goes?
Do you mean ground versus a space-based?
Yeah.
So the JWST, the James Webb Space Telescope, started delivering images early this year, I think, or late last year. And they've been, just absolutely stunning. And it's a perfect example of why we build bigger and bigger telescopes. And in fact, why we want to build the Giant Magellan Telescope. For ground-based telescopes, it takes about between 20 and 30 years to develop a generation of telescope. The last generation of telescopes were 8 to 10 meter apertures, and those went into operation in the early 90s. And in the early 2000s, a lot of the same people who had built the 8 and 10 meter telescopes said, well, we got to start thinking now about the next generation. And so the Giant Magellan Telescope project started actually, I think, in 2003. So a little more than 20 years ago.
Yeah.
But you basically already, described the reason it makes sense to build the ground-based telescopes, and that is that we can build them much larger at much lower cost. So we can build more of them. We can deliver a larger aperture, which means better collecting area, a higher resolution limit, and we can modify and upgrade the observatories over their lifetime. That was possible with the Hubble Space Telescope because it was, in Earth orbit. But at the moment, we have no capability to service or upgrade the James Webb Space Telescope because we have no way to get people to the second Lagrange point and bring them back.
Yeah.
So it's fantastic to have space-based telescopes. And one of the things that they can do is look at the wavelengths that we can't observe very well from the ground, and in particular the ultraviolet and some parts of the infrared spectrum.
Yep.
But in general, for the full optical and infrared range of wavelengths, we can do better from the ground because we can correct atmospheric turbulence, and we can build a much, much larger telescope.
Yep. And so I think it's important to point out, you talk about the advantages of having the ground-based telescopes, but the enabler is what you've mentioned around the technology and its advances and the manufacturing abilities, the ability to make those precision mirrors that, we couldn't have done what you're doing today 30 years ago, right?
Yeah, I'm trying to remember. I think that the University of Arizona has produced 9 or 10 8.4 meter mirrors now. They produced the combined primary tertiary mirror for the Rubin Observatory. They produced 2 8-meter mirrors for the Large Binocular Telescope, which is in Arizona. And now they've cast 7 mirrors and finished 3 of them for us. So, essentially the risks associated with producing our mirrors, the technical risks, the cost of schedule risks, have all been eliminated. We know how long it takes to make a mirror. We know how long or how well the mirrors can be made. Yeah. So certainly the production of the primary mirrors is a key technology, but that technology has been evolving for quite a long time now. And it did exist. It did exist 25 years ago.
Okay. Now, you mentioned the images that James Webb has been delivering, and my understanding is it's already kind of shaking some foundations of what we understand about the universe.
I mean, I'm
right?
not an astronomer. My background is in engineering and physics.
Yeah, me too. but I read.
But I've read. It's one of the amazing things about astronomy is that discoveries wind up on the front page of the New York Times.
Yeah.
Or your favorite newspaper, and that's unusual. You don't see giant discoveries in chemistry or biology making the front page. There's something about astronomy and the fact that we can all engage with our eyeballs with the sky that seems to make those astronomical discoveries resonate with everyone in a way that the other sciences, I think, struggle to resonate. Yeah. But yeah, I mean, the JWST has discovered galaxies that seem to me much more mature than they should be for the age of the universe when they appear. They've discovered giant black holes that seem to be much bigger and more mature than they should be, based on the time span from the Big Bang to the age of those black holes. Yeah. So it's really exciting. And this, we're designing and building the Giant Magellan Telescope with a science case. Yeah. And we need to have some scientific objectives to help us sort of scope the wavelength and the size and where we put the telescope and the type of optical design. And those things are, for example, to try and better understand the nature of dark energy. And dark energy is the term astronomers use for the fact that the universe is not only expanding, but its expansion is accelerating. And that is a counterintuitive result. Right. And it's a very hot topic in astronomy and astrophysics. Yeah. Similarly, the development and the evolution of galaxies is very intimately intertwined with dark matter and we've got a name for dark matter, but we don't have a good framework for what dark matter is.
Right. Yeah.
There's a huge amount of interest, in humanity at this point for discovering life outside of our solar system.
Yeah.
And it's been a revolution over the last 20 years in the discovery of extrasolar planets. And this was sort of a pie in the sky idea for a long time, but it's been 20 years or so now since the first extrasolar planets were detected. And now we've detected literally thousands of them. And so now we're not just, trying to find them, but now we're trying to understand how planetary systems develop and evolve. And one of the features that the Giant Magellan Telescope will enable is the measurement of the chemical constituents of extrasolar planet atmospheres. And when you can now start looking into the atmosphere of the planet, you can look for biomarkers that would indicate, plant life, animal life, the sorts of life that we are familiar with, do create signatures in the atmosphere that we'll be able to look for.
Yep. And so it's not just about cool and more complete images, but it truly is going to enable us to understand our universe better.
Well, absolutely. And just like we've seen with the James Webb Space Telescope, that telescope also was, conceived and designed with a science case.
Yep.
But very quickly, the science case gets blown out of the water by the unexpected discoveries.
Right.
And it's so telescopes are often described as discovery machines.
Yep.
We design and build them with a set of capabilities that we know will answer some current science questions, but we also count on the fact, and everybody's in many ways most excited about, the unexpected discoveries that the telescopes will make. Yep. And that's been a consistent feature of each step in the generations of the telescope. Each time we go to a 2 or 3 or 5 times larger telescope, we discover a whole bunch of new things that were unexpected.
Yep. So I mentioned when I first started, you hit a milestone, and that's all about the telescope enclosure that's going to go down in Chile. So tell us about what happened with that.
Yeah. Okay. Well, we're all familiar, have seen pictures of radio telescopes and millimeter wave telescopes, which can operate day and night and are insensitive to exposure to the sun. Optical and infrared telescopes, that if you shine the sun on the mirror, you create an opportunity, you concentrate a lot of energy. And so solar telescopes are a very special beast to be able to actually point directly at the telescope. So optical and infrared telescopes need protection from the sun and from bad weather. Protection from the sun during the day, obviously, and bad weather whenever it occurs. And so historically, the enclosures for a telescope for 100 years were dome shaped, and that dome shape comes about from the angular motion of the telescope as it points around the sky.
Yep.
For the Giant Magellan enclosure, a dome is not a good shape for the type of telescope that we have and the ways in which we have to be able to maintain the telescope. And a key feature of the Giant Magellan Telescope enclosure is that it has a 75-ton bridge crane, 200 feet up at the very top of the enclosure, that we use to remove and reinstall the primary mirrors on the telescope. So every 3 or 4 years, the mirrors have to be removed from the telescope, their reflective coating removed from the mirror, stripped from the mirror, and then very carefully cleaned and put in a giant vacuum chamber, and a new reflective coating is deposited, and then we bring that mirror back to the telescope.
Got it. Yep.
So the telescope enclosure provides a lot of different functions. The bottom part, which is about the height of a 3-story building, is fairly conventional steel and concrete construction. And it has rooms and places for people to work, places for people to service the instruments and parts of the telescope. The lower enclosure includes a control room where a group of astronomers and technicians can operate the telescope at night. But the upper, the enclosure overall is about 65 meters tall. And the upper 55 meters of it is not a building. It's really an automated, mechanized environmental control system for the telescope.
Yep.
So if I move my head here, one of the features that you can see are a lot of those little windows or openings. Those are called wind vents. We have about 400 of those wind vents, and those allow us, as the telescope points in different directions and up and down, in different orientations to the wind at the site, we can open and close those wind vents to balance the airflow around the telescope, and control and attempt to control the temperature variations of the air in the enclosure. So we want a very small temperature variations. And let me just back up for a second, explain that. Well, we've all had the experience of driving down a road on a hot day and seeing the shimmering of the air above the road.
Right.
And we see that with our eyes at the level of, maybe a 20 or 30 or 40 degree temperature difference between the air and the hot road. The telescope is sensitive to that effect, looking through the atmosphere at fractions of a degree in Fahrenheit.
Right.
So ideally we have the telescope and the enclosure and the air and the optics all at the exact same temperature, and that's how we deliver the best possible image quality.
Yep.
So a big part of the enclosure's job at night is to balance not too much wind, because we don't want so much wind that we shake the telescope, but enough wind, enough airflow through the enclosure and around the telescope to stabilize the temperature as best we can. So there's these daytime, during the day, we control the environment around the telescope. We air condition the observing chamber where the telescope is located, so that we have the telescope at the nighttime temperature, ready to go. As soon as it's dark enough to start using the telescope. And another feature that is kind of mind-boggling, and again, I'll move my head, but so this is a 65 meter building, about 22 stories tall. So next time you're out driving around, spot a 22-story building. Imagine that building about the same width as it is tall, and then imagine the upper, what do we want to say here? The upper 19 stories of that building rotating, and not only rotating but opening in a similar way to the way a stadium roof opens. We have to be able to open the upper portion of the enclosure, of course, at night, so the telescope can view the sky. So there's the upper enclosure belongs to a class of things called heavy movable structures. And this is a gigantic movable structure. The upper enclosure weighs about 5,000 metric tons. It has to be able to move in rotation to keep up with the telescope as it acquires new targets. And that speed results in the need to be able to do a full rotation in about 4 minutes.
Wow.
So again, now imagine a 22-story building rotating on its foundations in 4 minutes.
Yeah, amazing.
These are some of the characteristics that make it such a challenging and interesting project in terms of design and fabrication, manufacturing, assembly, and then integration and verification and commissioning, which is the final phase at which we turn over the enclosure to the use for astronomy.
Okay, and so you've got that final design review done now? Is that what I understand?
Yeah, so the enclosure design has gone through multiple generations and concepts. It's the initial concepts for the enclosure started in the early 2000s. A little over 2 years ago, so we developed internally and with a company called M3 Engineering, based out of Tucson, Arizona. We developed the preliminary design of the enclosure. And then a little over two years ago, we awarded the final design of the enclosure to a company called EDOM. EDOM is based out of Bilbao, Spain. And so we've been working with EDOM for about 2.5 years. In May, the last week of May this year, we held the final design review. We called in an international panel of 10 subject matter experts. And, it's interesting to think about, well, why on earth do you need 10 people? Well, we needed people who were experts in civil engineering, structural engineering, mechanical engineering, electrical engineering, optical engineering, controls engineering. We also have some very complicated liquid and gas-based refrigeration and cooling systems. Not an obvious feature of an observatory, but I did mention that we have to air condition the enclosure during the day. And so we have literally a giant, a 1 megawatt level air conditioning system for the enclosure. And that's quite a and we're talking about air conditioning a 65-story building from a single physical plant, which you can see off to my right shoulder here. So we consume a huge amount of power to deliver that cooling. And then we have to exhaust that waste heat away from the telescope so that the waste heat doesn't interfere with the telescope's view.
Yeah, fascinating stuff. All right, so you've got the design review done. I assume that means you're about ready to start construction then, right?
Well, not quite, but it depends on what you it depends on what you call construction.
Okay.
So there's a variety of ways for delivering a construction artifact like this. And one process, in fact, the process we're using for the telescope is called design build, where you award a single contract to a company that or a collaboration of companies who can do the design work and the fabrication work. And we did that. The Giant Magellan Telescope awarded a contract like that for the telescope. And the telescope was designed by a company called OHB in Germany, who teamed up with another company called Ingersoll Machine Tool, based in Illinois. And they've completed the final design and actually started the fabrication before the final design was finished. And in a design build contract, you can do that simultaneously, that simultaneous designing and building process.
Got it.
We chose not to use that approach for the enclosure, so we're following what's called a design bid build delivery process. And that means we take the design to 100% completion, meaning all the design work is finished. And the final product of that final design phase are the construction documents, the drawings and specifications that describe every piece of the enclosure. And then we will go through a 12 to 18 month international competitive procurement process to identify, the best candidates and the best proposals to do the construction work. And we're starting that procurement process this year.
That's your next big hurdle.
That's the next big hurdle. It's not so much a hurdle. It's actually one of the most exciting phases of the construction process.
I bet. Yeah.
Because now we're going to get to engage with internationally the best construction contractors in the world for doing complex projects like this. And I personally think that's going to be a really exciting process.
Excellent.
It'll then take us probably somewhere between 6 to 18 months to evaluate the proposals and make an award. And then we can sign a contract and start the construction work. But that's still a couple of years away.
All right. So, thinking about just the function of the telescope and the advances it represents, what do you think, like, the biggest opportunity from a science perspective that's out there that this might go after?
Well, I mentioned some of those things before. I mean, we do have
kind of thinking, what's number one?
A dozen science cases. My guess, number one, just given, I think, the excitement in both the astronomical community and in just the human community at large, is extrasolar planets and discovering signs of some sort of life, outside of our solar system. We haven't really discovered signs of life outside of our planet yet.
Right.
Although there's
exactly.
lots of suspicion, right, about what might be on Mars or on the
Mhm.
moons of Jupiter or Saturn.
Mhm. Yep.
But this is really, this really goes to the heart of, who are we? How did we get here? What is our place in the universe? What is the life cycle of the universe? How does the universe start and how does it end?
Yep.
Those are really the giant questions that a giant Magellan telescope can attack.
Yep.
And of course, the scientists just want us to hurry up and get the thing built.
I'm sure they do. Yep.
Because they're just being tormented by these new
Oh,
discoveries. So JWST can identify things that it can't necessarily fully characterize,
mhm.
and we really need the Giant Magellan Telescope to, when JWST or the Rubin Observatory says, here we found something really interesting, but it's really small, it's really far away, and we've been able to detect it, but we
Right.
can't characterize it.
Yep.
And that's where the Giant Magellan Telescope really will come into its own.
Yep. So you got the
And the
scientists
real,
champing at the bit.
yep,
Yep.
and I just want to say, Jim, that
Yeah.
the telescopes do two things primarily. They create just simple images of the sky, and we've seen those spectacular images coming out of JWST. But they also, the instruments on the telescope, the most important and productive instruments on the telescope tend to be the spectrographs. And we have optical and infrared spectrographs that can take the light from a star or a galaxy or a red blob that we don't know what it is, and split that light into its constituent colors, where each of the colors or combinations of emission lines, these are colors that are associated with atomic transitions in the chemical elements,
Mhm.
that through the spectroscopic analysis, that's how we determine, well, is there oxygen? Is there
Right.
nitrogen? Is there
Yep.
hydrogen?
The
And those things are,
characterizing that you mentioned earlier.
sorry?
The characterizing that you mentioned
Yeah,
earlier.
the characterizing is really done with the spectrographs.
Yep.
And the 25-meter telescope is able to do spectroscopy on objects that are out of the reach of the JWST.
Yep. Got it. Very cool stuff. Well, we are just about out of time. Is there anything, Bruce, that we haven't covered that folks out there should know about the Giant Magellan Telescope?
Well, if you would indulge me a little bit, I would just like to talk
Absolutely.
about some of the technologies that are involved
Yeah.
in delivering an enclosure like this. And I've read through some of your Forbes articles. I've looked at some of your other podcasts. And how we design and manufacture a monster like this is, we're using essentially all the cutting edge technologies.
Mhm.
We're using something called building information modeling or BIM modeling,
Yep.
where we combine the electrical systems, the control systems, the structural systems, the mechanical systems into a giant integrated model. And I'm sorry, I can't pull it up and walk you through it, but it literally has every light switch, every doorknob,
Yeah.
every pipe, every hose, every nut,
Yep.
every bolt.
A digital twin.
It is absolutely a complete digital twin.
Yep.
And we will use it not only we'll update that digital twin during the construction process,
Yep.
so that at the end of construction, we not only know that, over here we have a 5 horsepower electric pump, but we actually know the manufacturer and the part number and the serial number,
Mhm.
so that when it comes time to service that pump, we can use AR, augmented reality or virtual reality tools. Somebody puts on a pair of goggles, looks at the pump, sees the part number, sees the reference to the documentation. And this feature is what will help us, stay online and observing,
Right.
hopefully, when the weather allows, something like 330 nights a year.
Yep.
So we would operate, the observatory operates 24 hours a day, 365 days a year.
Yep.
And so having that ability through the computer models to identify the problems and organize and schedule the maintenance is a huge deal.
For sure. Yep.
There's another really interesting aspect to this for me, which is designing for fabrication and designing for assembly. And these concepts are built into your cell phone. A friend of mine likes to say that you can't get a grain of rice into a cell phone because the insides of the cell phone are so compact and so filled with components. So designing a cell phone or an enclosure for how you fit all those pieces into that space is a design for manufacturer problem. And so we've got to build a 65-meter Giant Magellan Telescope enclosure on a mountaintop that's 2.5 hours from the nearest city. And we're about 2,500 meters or 8,500 feet in elevation. So we're constructing in a very remote and somewhat hostile environment. And that means you want to do the minimum amount of actual fabrication and construction work at the site as you can. Yep. And so one of the strategies that we use and we've incorporated into the design is modularity. So we want modules that can be assembled in a factory, shipped to Chile, trucked up to the site. And then mainly what we do at the site in terms of constructing is assembling. And so the upper enclosure, I believe, has about 10 levels in it. And structurally, and in terms of the cladding and those wind vents I mentioned, those components are all modular, so that they can come up on the back of a 40-foot truck trailer. They can be offloaded at the site and then craned to the summit and installed and assembled on the telescope. So that designing for fabrication, designing for assembly, use of modularity, these are all very current sort of, the same sorts of technologies that Boeing uses to design and assemble airplanes. We are using to design and build the Giant Magellan Telescope enclosure.
Marvelous. Yeah. Excellent stuff, Bruce.
Thank you.
Thank you. I appreciate you being here.
Well, it's once you get me started, Jim, you can't shut me up. So.
No, I understand. You and I, both engineers, we could geek out on this all day, couldn't we?
Yes, indeed.
Well, definitely. Thank you for sharing the story of the telescope, and I look forward to continuing to following its development and construction.
Yeah, well, I'd love to talk to you again in a year or two when we've got this monster coming up out of the ground. So stay in touch.
Let's plan on it. Good deal. And of course, as always, thanks to those of you in the audience. This was just, to me, a super fascinating and illuminating story. I can't promise every story we have is going to be quite that illuminating or fascinating, but they're all going to be at least a little bit of both of those. So we're here every Tuesday. Join us next week. We'll have another show for you. Thanks for joining. And thanks again for Manufacturing Talks. So long.
Thanks again, Jim.
Thanks for tuning in to Manufacturing Talks with Jim Vinosky. Watch for new episodes dropping every Tuesday. And don't forget to like, share, comment, and subscribe.